Welcome to this lecture series in general topology. In this lecture, we'll be discussing arbitrary products of topological spaces. We have previously seen how to product finitely many topological spaces. But now in this lecture, we will be going completely general and talk about arbitrary products. All right, so let's recall a little bit. The main challenge here is that of notation and familiarity rather than actual mathematics. So fix a finite set, and suppose we have a collection of topological spaces indexed by the finite set S. For every element of F, we have a topological space X alpha. Then we write this symbol. This thing is meant to denote the product of all the X alphas. And what does that mean? What is this as a set? We talked about this. So as a set, this is the set of all functions from F to this union, set of all such functions with the property that an element beta of F is mapped to an element of X beta. So let's call this phi, or maybe, phi is better perhaps. So phi beta should map inside X beta for all beta in F. So the collection or the set of all such maps is this thing. And this may sound like a very unnatural thing because products or elements of products are typically thought of as tuples. But you can easily think of such a thing as a tuple, as we talked about. So you can think of this as the following tuple. You can think of it as, suppose we write phi of beta as little x beta. Then phi can be equivalently written as this tuple. The advantage of doing things this way is that we do not need an ordering on F. If F were an ordered thing, for instance, if F were 1 up to n, then this tuple is the familiar way of writing things. You can just write this tuple as x1 up to xn. This is something that we are familiar with. We are just generalizing that or relinquishing the orderedness or the requirement that F be ordered and still retaining everything of value. All right, so that's a set. We know what that set is. And the product, so we'll talk about the product topology, and I'll recall the product topology. So we have recalled this. And now, what are the projection functions? So for every element here, suppose you pick an element, this thing in the product, you can project it out to the beta coordinate or the betath coordinate, as we say. You just retain the element corresponding to beta, right? So we have these projection maps. And now we don't need to write this one more time. So now we can talk about the product topology. The product topology on this object, and if we haven't said anything, we will always be considering the product topology. If we do not further qualify as to what topology we are talking about on this guy, then we will be working with the product topology. So the product topology here was defined as the coarsest topology, which makes each of these projections continuous. So I'm not writing all that, but that's what we did. And then we discussed, very importantly, the universal properties. We discussed the universal property, not universal properties, but universal property of the product. So we discussed this. What was it? Maybe I should first talk about basis and subbasis, and then I'll come to the universal property. So what did we say about the basis? So what you can do is for each X alpha, you pick an open set in X alpha and you product all of them, right? So this product is a subset of capital X. And you can write it that way. I mean, this product is nothing but this intersection, something that perhaps I did not emphasize enough in the previous lecture. But this intersection is nothing but this product. And the collection of all the things that you get that way is a basis for the topology, for the product topology on X. So this is something that we said. And a subbasis is obtained in this way. For each beta, you collect all such things, right? Where U beta is an open subset in X beta. So you vary over all open subsets in X beta and take the pre-images of all of them under the beta ith projection, collect them in a set, and then union all of them as beta varies over F. That is a sub-basis for the topology on X. So we have that, and then we talked about the universal property. And one way to express the universal property was that if we have topological space Z, and we have continuous functions from Z to X alpha for each alpha, then there is a unique continuous function to the product. There is a unique continuous function to the product of all of them, such that this diagram commutes. So once you have defined continuous maps into each of these spaces, you have kind of stitched them together uniquely. There is only one way to stitch all those maps together to map into this big gigantic object, or to the, not a very gigantic, but certainly a bigger object than each of these X alphas. So stitch them together to get a unique map such that this diagram commutes. So that was the universal property. We again talked about it in great detail, but now we will be generalizing all of this to arbitrary products. All right, so let's move ahead. Some problems for practice. We have proven a lot of results like this for real numbers. If you replace C with R, we have proven all of them. This time, as exercises, I am just leaving them or asking you to prove them for complex numbers. No new difficulty will arise. It's just that it is good practice. It will help you digest the definitions. So do not ignore any problem. Okay, let's move ahead. So we need to talk about arbitrary products. What you have is, again, a collection of topological spaces indexed by some set J. The set J is no longer required to be finite or countable even. It could be an uncountable set. So let me maybe emphasize that. Here J is, oops, what have I done? So here J is possibly uncountable. Even though we will be mostly working with J being countable, but there is no such restriction. J could be an uncountable set. All right, so now you have a collection of topological spaces indexed by a set J. Also, we are not requiring that these be distinct for distinct alphas. They could, for all purposes, be the same space repeated for each alpha. It could be just that X alpha is equal to X beta whenever alpha and beta are chosen from J. So we are not requiring these to be distinct spaces. These are just some family of spaces indexed by the set J. Okay, so let X be the product of all of them. This is right now just a set. And we have talked about what this means. This is the collection of all functions from the set J to the union of the X alphas with the property that beta maps inside X beta. So the image of beta goes inside X beta. In the tuple notation, any element here can be written as X alpha, then you put a colon and then alpha in J. So this just means the function which sends alpha to this element. All right, so this is the collection of all functions of blah, blah, blah nature. And now we define the product topology on this gigantic space or set as, no surprises, you can finish this statement yourself, the coarsest topology on X such that each projection, or maybe let me write such that pi beta is continuous for each beta in J. It's the exact same definition as we gave for finite products. Nothing changes. So pi beta, I'm sure you recall, pi beta is the projection onto X beta, which takes an element of X. If we write it as this tuple, it just maps that tuple to X beta. The x beta coordinate of this tuple is retained by the projection. Everything else is forgotten. Okay, so we define the product topology on X as the coarsest topology which makes each projection happy. Okay. All right, so yeah, that's the definition. Do I need to say anything else about this? I don't think so. Okay, so let's move on. As usual, we'll be talking about a suitable basis for the product topology. Fix, again, a collection of topological spaces indexed by some set J. Let X be the product of all of them. And let beta, or not beta, but script B, sorry, this is not beta, this is script B, be this thing. Read this. Let me not read it out. Pause the video and read it. What is this? Okay, let me read it. For each alpha, you choose an open set in X alpha. Take the preimage under the alpha's projection of U alpha and intersect all of them. Remember what we did in finite products. Then okay, let me say this. So then we say B is the basis for the product topology on X. Or is it? This is what we would have liked to said, or this is what we would have written if we, were not thinking too much. If we were to guess a basis, we would have just immediately guessed this as a basis. But this is not a basis for the product topology. This will, if you take this is a basis, but not a basis for the product topology. The topology generated by this basis is much, much finer than the product topology. So no, this is not a basis for the product topology. We'll have to modify this set. So what is the basis? The basis is there is a finite set, or yeah, how to write this? Let me see. Yeah, so let me write it that way. So U alpha is open. U alpha is open in X alpha for each alpha, and very important, and there is a finite set S contained in J such that U alpha equals X alpha for all alpha not in F. And when you first read it, it looks like garbage, and I sympathize with you. So what is it saying? At least let us syntactically or semantically read it out. What is it actually saying? It is saying that you take the preimages of open sets in X alpha and intersect all of them, but you can only do this with the restriction that only finitely many of these U alphas are allowed to be properly contained in X alpha. All but finitely many of the U alphas are equal to the parent space. There is a finite set F such that U alpha is equal to X alpha whenever alpha is away from F. F is a finite set. So all but finitely many alphas have this property that the open set you chose is actually all of X alpha. Okay. So in particular, you could have chosen F to be a singleton. So then what will you be doing? What will this intersection look like? It will be just U alpha for the, let's say F is the singleton beta. So then this intersection is the product. Well, before even we go there, what is this intersection? This intersection is just the product of all the U alphas. So this intersection, just a fancy way of writing the product of all the U alphas. Again, this is something that perhaps I forgot to emphasize in the previous lecture, in the lecture on finite spaces. So here in this product, we are saying all but finitely many U alphas are actually X alphas. Okay, so this may sound strange and maybe even unsatisfactory, because the natural thing to ask for would seem to be the one where U alpha, all the U alphas are free to be open sets, any open sets in their parent space, but no. This is a very important difference, and I will leave an exercise here for you towards that. But for now, let's just prove it, prove the statement that has been written, and not worry too much about the intuition behind it. It is anyway very difficult to get an intuition about arbitrary products. Our relationship to them is somewhat formal and will be via universal property rather than visualization. Some infinite space, some infinite products we can visualize. We will see as we go along, as we proceed in this lecture series, we will be able to visualize some of them. But most of the time, it's just better to be able to work with them and use them rather than trying to visualize them. That's my suggestion anyway. It's not like I'm making a mathematical point here. All right, so how do we prove this? It's the exact same, ditto same proof that we did for finite space, finite product. So to do that, let tau, what should I write? Tau S be the topology generated by, why am I writing it tau S? Should be tau B, right? Let tau B, yeah, so even before that, note that this is a basis on the product. Not that it is a basis for some topology or anything. No, it is just a basis. Recall, given a set X, we have a notion of a basis on X. It's a collection of subsets of X with certain property, which I don't want to recall. So you can just, it's a purely set theoretic exercise for you to verify that this is a basis. And now let's say tau B be the topology generated by B, and tau P be the product topology. What do we want to do? We want to show that tau B is equal to tau P. Okay, both directions are easy, so let's verify to see why tau B is contained in tau P. Why is that? Well, each projection function is continuous under tau P. So what would you do if you want to prove this? You will pick some basis element and show that it is here, and that is sufficient to prove this. If every basis element is in tau P, the entire topology generated by the basis will be in tau P, something we have beaten over and over. So you pick an arbitrary basis element and just show that it is in tau P. And we know, we have exactly the description of the basis elements. So suppose you pick a basis element, only finitely many of these U alphas are proper subsets of their parent spaces. So let, it's not something I wanted to do, but let me do it. So to see this, let this thing be in this guy. And now each of these things is an open set in the set X, right? Why? Because pi alpha is a continuous function. Tau P was defined so that each projection is a continuous function. So each of these guys are open subsets of the parent space under the product topology. We are intersecting all of them. Now it is not true that arbitrary intersection of open sets is open. Only finite intersections of open sets are guaranteed to be open. But this is truly, or this is, if you think about it, only a finite intersection because of this clause. For all but finite, so there is a finite set F contained in J such that this happens. That's by definition of script B. For elements which are outside this finite set, what is this thing? This thing is pi alpha inverse x alpha, because U alpha is equal to x alpha for alpha outside F. But what is pi alpha inverse x alpha? What is this thing? This is the entire set X. So for all but finitely many of the elements in J, this thing is just the entirety of X. So not writing them will not change anything. right? So this intersection, which may look like an infinite intersection, is actually just the intersection of finitely many things, right? Where f is a finite set guaranteed, or it exists because of the definition of B. So this intersection is actually just a finite intersection for a suitably chosen f. Each of these are open, and hence this is an open set. So that's the reason why this thing is actually open in the product topology. So I'll not write anything. So what have I done? I have chosen an arbitrary basis element, and I have argued why that thing is actually in the product topology. And therefore, this containment has been justified. So let me not write anything, and you can write everything in your notes. And for the reverse, to see why tau p is contained in tau b, it is clear that every projection function is open. Every projection function is a continuous map under the topology generated by B. Right? Because you have this projection function. You want to show it as a continuous map. You pick an open set in X beta and pull it back. Now that thing is clearly here because except for beta, let f be this singleton beta, and for that f, this thing that you get here is exactly pi beta inverse of u beta. So this thing is clearly in the basis, and hence in the topology generated by the basis, right? So each projection function is continuous if you equip the set X with tau b. But what was tau p? Tau p was the coarsest topology which made each projection happy. Tau b is one such topology, meaning tau b is a topology which makes each projection happy, and therefore the coarsest one should be contained in it. So that is justified. I don't want to write all of this. Anyway, we have seen all of this reasoning before when we were discussing finite products. It's just that the context may make it look more complicated than it is because of the possible uncountability of J. All right, so I'm assuming you follow this, but take your time. Don't move ahead if this is not clear. Take your time. At least understand this on the formal level. Don't worry too much about the intuition as of now. We haven't seen any examples yet. As you go along and read more and more, you will develop better intuition for the product spaces, and at one point, this will be second nature. Taking infinite products will be nothing. So I mean, if I were a student, perhaps I would also be perplexed by all of this, especially because of the symbols. But in no time you get comfortable with these things, and then you see others suffer the same thing as you. So now for an exercise. This time again we have the same setting. We have a collection of topological spaces indexed by some set J. We have the product of all of them. And for each beta, define this thing S beta as the collection of all these inverse images. So in this whole thing, all you are saying is that f is only allowed to be a singleton. So what you get is f is only allowed to be the singleton beta. So what you get is S beta, and you're taking the union over all such things. This exercise wants you to show that this thing is a sub-basis for the product topology on X. So the topology generated by this particular thing, first of all, this is a sub-basis that you need to show. And then the topology generated by it is same as the product topology, right? So very simple exercise, very easy. And then I also want you to Google and read upon box topology. So before I corrected the description of B, there was something written there. There was a basis given there, and that basis is, or the topology generated by that basis is what is called the box topology, and that is useless for us. But still, you should know it. So Google, go to Wikipedia, maybe find some whatever, read your textbook. Maybe you would perhaps like to read Moncrief's. That's a decent book, very standard, or some other book you like. Okay. So let's move on. Most important, the universal property of the product topology. So the same thing, we have a collection of topological spaces indexed by a set J. We have the product of all of them. And whenever we have a product of topological spaces without any qualification, we will be assuming that the product is equipped with the product topology. All right, fix a topological space Z and suppose we have been given a map, just any map from Z to X. Then the following two statements are equivalent. The first is that f is continuous, meaning the given map is continuous. And the second is that the projected out version of f is continuous for each projection. So this was given to us, mapping into the product X. What you can do is you can compose it with the projection pi beta. If this is continuous, its composite with this projection will also be continuous because pi beta is continuous. F is given to be continuous, pi beta we know is continuous, the product topology is defined just to make the projections happy. So the composite will necessarily be continuous. So 1 implies 2 is clear. I mean, we are just repeating this lemma which we discussed in the context of finite products. So the other direction, suppose we are given that each of these are continuous, we want to show that f is continuous. Right? So how do we do that? Just give me 1 second maybe. Yeah, so we need to do 2 implies 1. 1 implies 2 I have already said in words, 2 implies 1. The same proof we saw for finite products. So what are we given? We are given that each projected out version of f is continuous. We want to show f is continuous. So to show f is continuous, you pick something in the basis or maybe even in the sub-basis. So let beta in f be fixed. Let u beta be open in x, at x beta. Okay, so here is what I want to say. Suffices to show that f inverse of pi beta inverse of u beta is open in Z. Why is that? Together these form a sub-basis for the product topology. This is the exercise on the previous slide. Right? If you vary beta and you vary u beta, the collection of all of them forms a sub-basis for the product topology. And if we are able to show that f pulls back elements of a sub-basis to open sets, then f will pull back every open set to an open set. Right? So that is something that we've already seen when we were discussing sub-bases. Okay, so this is enough. But what is this? This is equal to pi beta composed with f inverse u beta. But is it open? It is open in X because we are given that this is a continuous map. So that is the proof. In the previous lecture, we perhaps didn't do it this way. We did a little extra, but this is sufficient. Okay, let's move on. Another way to look at the universal property, just a repetition of the discussion on finite products. We have a collection of topological spaces indexed by a set J, not F, but J. And X is the product of all of them. And Z is a topological space. And suppose we have a continuous map going into X alpha from Z for each alpha. So this has been given to us. Maybe I'll write an alpha here. So for each alpha, there is a map going into X alpha, which is continuous. Then there is a unique continuous map F going from Z into the product. There's a unique continuous map F going from Z into the product such that the following diagram commutes. What diagram commutes? This diagram. Here you write pi alpha. Maybe again I will write beta perhaps, just to confirm to the writing in the pink. So this diagram commutes for all beta. There is a unique continuous function f mapping into x from z, which makes this diagram commute for all beta in J, not F. J. There is a unique continuous map here which makes this diagram commute for each beta in the indexing set. Right? Why is that? Well, just use the previous proposition. First of all, there is a unique map. Forget about continuity for the moment. We are given a bunch of maps from Z to X alpha. There is only one map which makes this diagram commute for each beta. There is only one such map, and you can explicitly write down that map. What is that map? That map takes Z to F alpha Z, alpha in J. That's the only map which makes this diagram commute for each beta, right? And now we want to show that it is continuous. If we show that this is continuous, this proposition will be proved. But now you use the previous, the proposition on the previous slide. What do? If you want to prove this is continuous, you just ask if the projected out version is continuous for each beta, but that is already given to be continuous. The projected out version is this map, which is already given to be continuous, and hence we are done. So nothing to do here. Okay. But yeah, so the point of this proposition is if you want to throw a continuous map into the product, don't do it. Don't do it directly. Throw continuous maps into the participating spaces. Automatically, you will get a continuous map here. Otherwise, you will be messing around with the horrible description of X. All right. Now for some examples. I don't know how enlightening this discussion is going to be, but I have to at least give some examples to do justice to this lecture. So first, what is this? We have this space 0, 1 with the discrete topology. So even before writing this, what do we have? We have this be equipped with the discrete topology. In short, we also may write, let this be a discrete space. And there is one way to write the same statement. Okay, and then what have we written? This is just a way to product natural numbers, many copies of this. So to be very formal, how would we write? What have I written? Define xn is equal to the same thing for each n. Repeat. For each n you have the same space. And now we have a family of topological spaces indexed by the natural numbers. So here J is equal to n. Just to correlate with the discussion that has happened. So we have a family of topological spaces indexed by natural numbers. And when we write this, what do we mean? What we have written is really product n in naturals xn. So this is just an alternate way of writing it, and it is not a bad way. When we write Rn, what do we mean? We mean R cross R dot 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 cross R n many times. And you may write it like this. Pi n in some, or not n, you would probably write k in 1 up to n. And then you'll write an Rn. This is a horrible way or maybe an unfamiliar way of writing Rn, but this is one way of writing Rn. Anyway, so the power notation is, what does it do? It just is screaming at 0, 1 cross 0, 1 cross 0, 1 natural number many times, right? That's what the power notation does. So I hope you're not thrown off by this. Okay, and this we equip with the product topology, of course. And let's say something about this. So what can we say about this? First of all, note that singletons are not open in it. So for example, think of this space, think of X as all the 0, 1 sequences. Every element of X is just 0, 1, 0, 0, 0, 1 something, right? all such infinite encoded messages, if you will. Right? You can think of them as encoded messages. Zeros, ones, and so on. So you can think of it that way. And a singleton will be a specific message. Or you can think of these as coin tosses. Infinitely many coin tosses. Every possible outcome of heads and tails is sitting here. But that is going into probability theory. Yeah, so singletons are not open. So you fix a singleton. Let's say we fix this very simple singleton, which is all zeros. This is an element in the product. We are saying that this singleton set is not an open set in the product topology. Were it open, it would contain a basis element. But as we have seen, if you have a basis element, all but finitely many, okay, maybe I'll have to write something. So let's say, so suppose this were open. If this were open, were open in X, then there would be a basis element, which we can write like this. Some basis element pi n in naturals, un is contained here, right? Where what is un? Un is an open set in the space xn, where all but finitely many of the uns are equal to the entirety of xn. Right, so all that I mean, since this is a basis element, all but finitely many of the uns are equal to this thing. And then you can just easily see that some element here will have a 1 infinitely many times. Right? Because beyond a certain point, let's say beyond n equals 5, this is just the entirety of xn. So this you can write as, just as an example, this might look like U1 cross U2 cross U3 cross U4 cross U5, but then after that all you see is this 0, 1, the entire xn. Right? So clearly the elements in this, or there is an element here which has infinitely many ones, and therefore it can't possibly be here. In fact, as soon as you have 1, 1 somewhere here, there is no way it is equal to this element, and hence this containment cannot hold. So this singleton is not open, and similarly you can show no singleton is open. Anyway, just some understanding, some intuition that we are developing. Think about this. Maybe what I said is not making it very, very clear. The way to get this is to follow the definitions for yourself and think about this. That's the only way to get it. Another remark I want to make is the shift map. So what is the shift map? So we need to define the shift map. Define t from x to x as t of this tuple is equal to this tuple. I'll erase this part so that there is no confusion. So what is it doing? It's kind of shifting time. If you think of natural numbers as time, the message that you received at time 1 is x1, the message you received at time 2 is x2, message you received at time 3 is x3. So this is containing the present and the future. If you move 1 unit forward in time, this becomes your present, and then everything else is the future. So this is an x4. Yeah. So it's kind of shifting time. This t you can think of as a time map. So this is also called the shift. I mean, this is called the shift map. This is called the shift map. And the shift map is continuous. How do we show such a thing? So we have a map from some space to the product. Right? We have a map from some space, which happens to be the product itself. That's okay. We have a map from some space to the product. How do we show it's continuous? We show its projected versions are continuous. So let's project on the kth coordinate. And what is this map then? This map, first you have this infinite tuple x1, x2, x3. That becomes x2, x3, x4, x5. And then if you project out on the kth coordinate, what do you retain? So here you have x1 up to x2, x3. Then that becomes x2, x3, x4 up to dot dot dot. So the first coordinate here is x2, the second coordinate is x3, the third coordinate is x4. So what is the kth coordinate? So if you hit it with pi k, you get the k plus 1th value, right? If k were equal to 1, you would have gotten x2 and so on. So what is this composite? This composite just is same as pi k plus 1. So this composite is a projection and hence continuous. All projections are continuous. And therefore T is continuous. Right? So again, some relationship we are developing with the infinite product via these small things. Great. So here is a sort of a different version where you have the indexing set is all the integers rather than naturals. So in the coin toss analogy, you can think of this as, past and the future. If you think of that as time, the negative indices are the past and the positive indices are the future. The index corresponding to 0 is the present. Here we were taking the index corresponding to 1 as the present, but this is much more natural in that way. The index corresponding to 0 is the present. And these are all possible histories and futures of and the presents of an infinite coin toss. Okay, and the same comments apply. No singleton is open here and the shift map is continuous. So what is the shift map? Let me just define the shift map and leave other things as exercises. So what does it do? It takes an infinite tuple, which I will write in this way, and outputs an infinite tuple like this. May look very confusing, but what is it trying to say? At n is equal to 0, what you see is x1. So you've moved one unit forward in time. Here n equals to 0, you see x0, but here n equals to 0, you see x1, and so on. And this is not forgetting any data. This was a forgetful shift. This shift map was forgetting what happened. Like there is no way to recover x1 from this. But using this, you can recover what happened at x1 or x0 or whatever. Like this is not forgetting any information. This is forgetting information. That's okay. Prove that this shift map is continuous in this setting. The same kind of approach will give you. Don't try to pull back open sets and all that. You can do that, but I think it's inefficient and messy. And also prove that singletons are not open in this space. Okay. You can generalize everything to finite sets. Fix a finite set A. Again, equip this with the discrete topology. You can talk about this. So here you don't, there was no sanctity of zeros and ones as numbers. These are just some letters. And now you can think of this as an infinite sequence of messages that you receive. At every point of time, you receive a message, a letter. And so this is some space, and the same things you can prove for this more general object. In fact, you can also think about generalizing this. Here it doesn't necessarily have to be time. You can have some spatial thing here. And think about this. Maybe in future, or definitely in future, we will talk about such things. We could have talked about it right now, but I don't want to make it too rich of a lecture. Anyway, so think about this. And maybe I think I have one more example. I have at least one more thing to talk about. Maybe I have more. Let's see. So this time we have any set S and a topological space Y. And we define X as the set of all the maps from S to Y. So the first thing I want to say that this is same as this product. Because what is this product? What did we say about product spaces? So first, let me, to explain this, let's define Ys is equal to Y for all S. So we have a family of topological spaces indexed by the set S. And then this product we can write like, whoops, we can write like this. And what was this? What did we say about this? This is the set of all maps from S into the union of all the YSs, but the union of all the YSs is same as Y, such that the image of S goes inside YS, but YS is Y. So this is precisely the collection of all maps from S to Y. So this is an equality. There is no identification or change of perspective or anything. This is exactly equal. And hence, we can endow this with the product topology. This is the product of S many copies of Y. So we can endow this with the product topology. Right? So I don't have anything more to say about it. It's just that the set of all the maps now from a given set to a topological space can be equipped with a product topology. The examples that we saw in the previous slide were certainly of this form. This space 0, 1 to the n was nothing but the set of all the maps from natural numbers to 0, 1 and so on, right? So there is nothing that I want to say. I mean, usually and many times we'll have the opportunity to work with these spaces, and endowing them with suitable topologies will be important. The product topology will be very useful. Okay, let's see if we have anything else. Yeah, we do have one more thing. So this is a general abstract result. We saw this in the context of finite spaces. We have a set J indexing two families of topological spaces. For each alpha in the indexing set, we have been given a continuous map. Then you can product the maps. So this map is taking the product of all the X alphas to the product of all the Y alphas, and this is the definition. I don't want to rehash it. We have done it in our previous lecture. And then this is also continuous. So the product of a bunch of continuous maps is also a continuous map, is the t-shirt version of this statement. And the proof is essentially this diagram. If you're stuck, you can go back to the previous lecture and see the reasoning there and export it here in the context of infinite, or rather arbitrary products. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.